Hi everyone. I'll be talking about a work teaching Transformers Causal Reasoning through Axiomatic Training. A work done at Microsoft Research India with my collaborators Abhinav Kumar from MIT, Gowtham Reddy and Vineeth Balasubramanian from IIT Hyderabad, and Amit Sharma, my mentor from Microsoft Research India. Now, in this work, we propose Axiomatic Framework, a new paradigm for training language models for causal reasoning. We train a 67 million parameter model from scratch on simple causal chains, which outperforms billion scale LLMs like Gemini Pro and Phi 3, and also rivals GPT-4 in inferring cause-effect relations over complex graph structures. Following Udiapol's axioms of causal irrelevance for structured causality rules, which informs our idea of teaching transformers from passive data via symbolic axiom demonstrations directly, instead of axiom-derived data unlike typical ML models. Now, using axiomatic training, we show that a transformer can learn causal axioms to infer cause-effect relationships and causation from correlations, suggesting how GPT-4-like models can learn causal knowledge from web data through noisy axiomatic demonstrations without intervention. In this work, we focus on the transitivity axiom of causal irrelevance as depicted in box numbered 1 in the poster, which could be easily represented in natural language. Following the stability assumption, for probabilistic models, we take the contrapositive of the causal irrelevance axiom of transitivity and generate synthetic data using that to train our transformer model. Our goal is to train a small decoder-based transformer to learn this axiom and apply it to highly complex causal structures unseen during training. Now, as can be seen in box number 2, we trained on symbolic demonstrations of transitivity in 3 to 6 length causal chains and found that the model generalizes to much larger networks even after we add permutations, reversal, or introduce complex branch graph structures, none of which were encountered during training. Following the example depicted in box number 3, our axiomatic approach breaks down each trained data instance into 3 parts: the premise, the hypothesis, and the label. The premise defines a causal sequence in natural language, followed by a question related to the premise. The label indicates whether the hypothesis holds true for the given premise. As shown in box number 4, we incorporate perturbations at different levels in the causal sequence of the training set to avoid models overfitting to spurious correlations. The perturbations are at 3 different levels. First is the edge level, where edges of the training sequence are randomly flipped with a probability of 0.5. Second, the node level, where the node names are randomly generated using alphanumeric characters made up of 1 to 3 characters length. And third is the length of the chain, which ranges from 3 to 6. Now, our train set contains short linear sequences of causal edges with structured perturbations. We train a 67 million parameter model on this dataset. As in prior work, we find that lack of positional embeddings aids generalizations. We also evaluate for sinusoidal and learnable PEs. Now, following the pipeline as shown in box number 5, we also test whether 3 different training sets in our pipeline, TS1, TS2, and OCC, on which we train a model from scratch separately. While all 3 have an equal number of data instances, which is around 175,000 in number, TS1 has more sequences with randomly flipped edges as compared to TS2. Only causal chains, or OCC, which has only forward sequential chains, makes up the third set of our training set. Now, through these training datasets, we are able to identify the effect of perturbation at the edge level and how much it aids or harms the generalization. Our model trained with no PE generalizes to longer sequences, even with shifted node names and changed order, such as reversal or shuffling. Despite only training on linear chains with branching factor lesser than 1, it generalizes well to large complex Erdos-Renai graphs with branching factors of 1.4 and 2. Now, while models with no PE generalize well to longer complex structures, SPE and LPE models struggle. They fail with longer node names, highlighting generalization failures with slight structural perturbations. Learnable PE experiences performance drops with sequences longer than 9 nodes. We also observe that while perturbations are important for generalization, after a certain point it starts hindering the generalization performance rather than aiding it. Our model, which did not have a single completely reversed sequence in its training set, generalizes well to completely reversed chains, outperforming models like Gemini Pro and Phi 3 while performing at par with GPT-4. As can be seen in box 6, our axiomatic training outperforms baseline language models at the core-to-cause benchmark by Zijing et al., which requires inferring causal relations from correlational statements. Model is trained on correlational statements of smaller graphs and evaluated on larger systems. Overall, we feel axiomatic training can be a promising approach to teach Transformers causal reasoning, and it marks a potential step towards a new scientific frontier at the intersection of causality and language models. Thank you so much.